Hello, Chemistry 12 kids. This is Mr. Chan again, and this will be titration calculation, titration curves, part number 2. Okay, so last day, remember, if I were to share the screen, remember we had talked about identifying titration curves. Okay, and so we talked about how the different types of titrations, whether strong acid, weak base, strong acid, you would get different titration curves, okay? And how you're able to recognize these 6 things on the titration curve. Now, hopefully you had a chance to play around with it, and hopefully some of you played around with this website. Remember I talked to you about that? And hopefully what happens is some of you played around with the acid, changed it to acetic acid, and you did your phenolphthalein, all right? And if you take a look at the titration curve, you will notice that it was very different compared to your strong acid, strong base titration curve, okay? And notice, hopefully you notice that where the pH was at equivalence was very different than if you had strong acid, strong base. Now, one thing I would like for you to be aware of is sometimes you actually get 2 equivalents. In this case, what you have is a diprotic acid. So a diprotic acid would be something like H2A. You could think of it like H2CO3. And if you were to actually take a titration curve, you would actually get 2 equivalence points. One is when you're going from H2CO3 breaking apart to H plus and HCO3 minus 1. And the other one would be going from HCO3 minus 1. You break down to CO3 minus 2 and H plus. Excuse me. But what you would get is you would get 2 equivalence points, okay? But right now, for Chemistry 12, all you need to worry about is you just have 1 equivalence point, okay? All right, so what I want to do is I want to approach this question that's at the end of your notes, okay? It says a sample titration calculation. It says a 50 mils of a 0.1 molar unknown acid is titrated with 0.1 molar NaOH, and the following titration curve is obtained. Confirm using calculations A, B, and C. What's the exact pH at equivalence, the half equivalence point, and choose an appropriate indicator. Now, in this particular case, you notice that the pH is 8.73. Okay, so because it is not a pH equal to 7, so therefore it is not a strong base, strong acid. And hopefully from your homework, you can recognize that the acid would be a weak acid. So your unknown acid here is actually a weak acid. Okay? And because it is one equivalence point, so it's a monoprotic acid. Okay? So the first step is, let's write out the equation here. So first step, we would have HA plus NaOH would give you H2O and NaA. Now, if we were to find the information here for our weak acid, we know that it was it is 0.10 molarity, and we have 50 mils. For the NaOH, if we take a look, we also know it is 0.10 molarity. And again, if we look straight down here, we find that it also took 50 mils. Now, if we looked at the number of moles, so we figure out the number of moles here, this would be 5. Let me see, I believe this would be, if I have a calculator, let me grab my calculator out. What did I do with my calculator? There it is. So I have 0.1 times 50 divided by 1,000. So this would be 0.005. This would also be 0.005 moles. And for NaA, this would be also 0.005 moles. Now, for the concentration of NaA, this would be divided by 0.1. So this would be 0.05 molarity. Okay? Now, this has been up until grade 11. Okay, in terms of stoichiometry, finding moles, mole ratio. Why was it 0.005? Is because mole ratio is 1:1. Now, we figured this out. Now what we have to do is we have to look at our salt. So this will be step 1. Step 2, we have to look at NaA. Now, NaA, if we have NaA, breaks apart to Na plus 1 and A minus 1. So the concentration here would be 0.05. This one would be 0.05. This one would be 0.05. Okay? Now, you might say, okay, what's going on here? Why do you have to look at NaA? Because we have to focus on the A minus 1. This one undergoes hydrolysis. Now, how do we know A minus 1 undergoes hydrolysis? 2 ways. Number 1, you can recognize that it is from a weak acid. So remember, anything from a weak acid will any conjugate salt from a weak acid will hydrolyze. The other way is by looking at the pH. So since there's pH is 8.73, something must have hydrolyzed. Okay? Now, in this case, it is A minus 1. So for step number 3, we do hydrolysis. So we have A minus 1 plus water would be in equilibrium with HA and OH minus 1. Now, how do I know that it is a basic reaction? And the reason being is because, notice, the pH is greater than 7. So it must have been a hydrolysis with water to produce a base. Okay? Now, so what you have is, again, oh my gosh, we got to set up our ice tables. Delicious. So I have A minus 1, yada, 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 yada. So this will be 0.05. You should be getting sick of this by now, people. This would be minus x plus x plus x. So this would be 0.05 minus x, x, x. Now, So you know that this would be Kb is equal to concentration of OH minus 1, HA, all over A minus 1. Now, but some of you might say, well, Mr. Chen, I can't find Kb anywhere. What on earth? Oh, but looky. I gave you pKa value. Okay? With pKa, you can find Ka. Remember, pKa is just negative log of Ka. All right? So to find Kb, we would use our pKa value. So remember, Kb is equal to Kw divided by Ka, which is equal to x squared in this case, all over 0.05 minus x. So we have 1.00 times 10 to the negative 14 divided by 10 to the negative 4.76 is equal to x squared all over 0.05. Okay, so if we did our calculation solving for x, so we have 1e negative 14 times 0.05 divided by brackets. Oh, shoot. Let's see. So you solve it. So 10 to the power of negative 4.76 negative is equal to, let me just work this out here, 1.00 times 10 to the negative 14 divided by 1.738 times 10 to the negative 5 is equal to x squared all over 0.05. So you solve for x, which is concentration of OH minus 1. So 1e14 negative times 0.05 divided by 1.738 e to negative 5. And then we square root it. So we get 5.36 times 10 to the negative 6. You have POH is the negative log of that, which is 5.27. So pH is equal to 8.73. Okay, so that's just to confirm it. All right, so again, basically you're looking at the titration curve to figure out some of the values, figuring out what undergoes hydrolysis, etc., etc., etc. Okay, hopefully that's pretty straightforward. This will probably be hint. You will probably need to know how to figure this out. Okay, now one thing I want to talk about is this. Let me jump to C. What is an appropriate indicator for this titration? What you want to do is you want to take a look at your acid-base charts, okay, your indicator, and you want one to sort of, that falls within that range of about 8.76. So for this particular equation, or this particular reaction, it would either be thymol blue, the base form, or phenolphthalein. So if we were to ask a question like this, I could say, I don't know, phenolphthalein. Phenolphthalein. Okay. Now, I want to go a little bit further and talk about B, what you mean by half equivalence point. And notice this half equivalence point is within this buffer zone. Okay? And what do you notice is this? at the half equivalence point, okay, this is where it's halfway to the equivalence point, okay? So the volume added halfway to the equivalence point. So when we talk about B, when we say half equivalence point, what that means is it is volume, half the volume to reach equivalence. Now, what's the significance of this particular point? So let's write out our equation again. So we have HA plus NaOH would give us water and NaA. Just like we're going to set it up, we're going to set it up like how we set up this equation here for number 1, but there's going to be a key difference. So here, if I write this down, this will be 0.10 molarity. This will be 50 mils. Here would be 0.10 molarity. This would be 25 mils. Now, slow it down here. You'll see a slight difference. Here, remember we talked about the number of moles? Here would be 0.005 moles. Here would be 0.0025 moles. Now, what's the significance of this? When at this particular time, notice the moles are not equal. So at this point, at this particular point, you will have 0 moles left here, 0.0025 left over, and at the NaA, you actually have 0.0025 moles made. Okay? Be very careful. All right? Here, at equivalence point, what would have happened is at this point, you would have had 0 left over, 0 left over, and 0.005 made. Now, what's the significance of this? Well, if we do the same thing and we find the concentration, here you divide it by 75 mils. Here you divide it by 75 mils. So what you have is 0.0025 divided by 75 times 1,000. So you get a concentration here of 0.033 molarity. Here would be also 0.033 molarity. Okay. Now, what you notice is you have a significant amount of acid and you have a significant amount of the salt with the conjugate base, in this case, HA and A. Notice, this is a buffer. So if we were to rewrite this, we would have HA plus water in equilibrium with H3O plus and A minus 1. Here would be 0.0, come on, pen, 0.033. Here would be nothing. Here would be 0. This would be 0.033. And remember, we have our ice. We have minus x plus x plus x. This would be 0.033 minus x. This would be x. This would be 0.033 plus x. Now, remember when we put it into our Ka expression, we can have Ka is equal to concentration of H3O plus A minus 1 all over concentration of HA. So what we have is we would have Ka is equal to X 0.033 plus X. This looks like your buffer calculations from before, minus X. And remember, to make our life easier, we can cancel out the X's, the change in X. So what we have is, if I use a different color, Ka is equal to X 0.033, and then you have 0.033. These can cancel out. So therefore, Ka is equal to X, which is H3O plus. So pKa is equal to pH. That's the proof. Okay?